Now let's use these Laplace formulas that we've developed or seen, at least, to do a couple examples. So keep these in mind and we'll refer to them as needed. But let's start by taking the Laplace transform of t minus 1 squared times the unit function shifted by 1. So looking back at this list, the one that matches most closely is the second one here, where you have f of t minus a and u of t minus a. So here we have f of t minus a is the t minus 1 squared. So what we need is, to match this, we're going to have e to the as, a in this case is 1, so e to the s, and then f of s, so the Laplace transform of f of t. So f of t would just be t squared, right? So this is kind of the part that maybe the most confusing on this is just matching up the pieces in the right way, matching up how to make this work. But with a little bit of practice, it's not too bad. You just have to find the right pieces and be careful. So again, matching this up, f of t minus a is this, and what we're looking for is capital F of s, meaning the Laplace transform of just f of t alone, not f of t minus a. So in this case, a is 1, so the Laplace transform would be e to the 1t, or e to the negative 1t rather. Don't forget the minus here. So e to the negative t, I'm sorry, e to the negative s. All right, we got it right now. E to the negative s, and then the Laplace transform of t squared, which would be 2 over s cubed. Right, remember t to the n goes to n factorial over s to the n plus 1. So there's the Laplace transform of this combination of f of t minus 1 and u of t minus 1. So just by matching it up, we can get that answer. And you could simplify if you wanted to write it a different way. You could, but I'll just leave it at that. Then let's try an example like this one, where we have cosine of t times u of t minus pi. And again, looking back at that list of Laplace transforms, we notice it matches this one here, where we have f of t now instead of f of t minus a. So the first one, the t minus a, matched in both of them. In this one, it does not. So we got to pay attention to this last, or this third Laplace transform formula. So in this one, f of t is cosine of t. So what we want is to take the Laplace transform of f of t plus a, where of course a in this case is pi. So we need to find a way to take the Laplace transform of f of t plus pi. Now unfortunately in our list of Laplace transforms we don't see anything like cosine of t plus pi or cosine of t plus anything. So we've got to find another way to approach it. And it turns out that it's simpler than you might think. If you look at the graph, for instance, cosine of t looks like this, right? Cosine of t plus pi shifts that to the left by pi, and so it ends up looking like this. And if you look closely, or maybe not even have to look closely, but you'll notice that that's just the mirror image or the negative of the cosine function. So it turns out that f of t plus pi equals negative well, let me do it this way, cosine of t plus pi equals negative cosine of t. So obviously this one is kind of conveniently arranged for us this way so that we can do it, but that's the general idea, is that the hard part with these is rearranging this f of t plus pi into something that we can do the Laplace transform with. If, for instance, it was like t squared and then you had t plus pi squared, what you would do is you would expand that out and then handle each term of the polynomial separately. So that would be doable. But this one we kind of had to have it set up carefully for us so that it works. So now that we have that, we are looking for, in our answer, this is going to be e to the negative as. A is pi, so this would be negative pi s, times the Laplace transform of cosine of t plus pi. But again, that's just the negative cosine of t, which means we'll have negative e to the negative pi s, and then the Laplace transform of cosine, which is just s over s squared plus 1. So there's the final answer, and again, you could rewrite it if you wanted to combine everything to one fraction or so on, you could. But that one illustrates how to use that third example up here, the third Laplace transform formula, when you have the product of a function and the unit step function. One last example here in this video. I want to do an inverse Laplace transform, and again look through the formulas we have there and see which is the closest. So we're doing the inverse Laplace transform of e to the negative 2s over s squared. So if we go up and look through here, you'll notice that it looks similar to the first one, but it's not quite because we don't have an s squared in the denominator, which tells us that it's going to be more like this formula, where f of s, capital F of s, will need to be the 1 over s squared. So that's what we're going to do. So we're going to think about this as looking like e to the negative 2s times f of s. So in other words, capital F of s looks like 1 over s squared, which means that f of t, the inverse Laplace transform of that, would just be t. And again, that goes back to the original ones we have on our Laplace formula sheet. That's one of the earliest ones we did. So again, going back and comparing here, we're looking for this form, and now we've picked out the right-hand side and sort of separated and tracked down the different pieces. So then what this is going to turn into, if we take the inverse Laplace transform, our answer is going to be f of t minus a times u of t minus a. So the inverse Laplace transform of this is going to be f of t minus a times u of t minus a, where f of t we know now is just t, and a in this case, notice that in the formula here we have e to the negative as. So comparing that to what we have here with e to the negative 2s, a equals 2. So if that's true, then our answer, f of t minus a, would be t minus 2 times u of t minus 2. So there's our answer. And if you want to see this written in maybe a more familiar form, this is the function t minus 2 that's turned off before 2 and turned on after 2. So before 2, the unit step function shuts this down and makes it 0. And then after 2, the step function turns on, and then you have t minus 2 times 1. So there's the answer for that one, doing the inverse Laplace transform. It's the same approach as always, where you're looking through your sheet of Laplace transforms and looking for what looks the closest, and then adjusting as needed to make the forms match up.